When we studied greedy algorithms, we looked at Dijkstra's algorithm for the single source shortest path problem. Now it turns out that Dijkstra's algorithm requires all edge weights in the graph to be non-negative. The Bellman Ford algorithm is a dynamic programming algorithm which allows you to compute the same quantities even if there are negative weights. So let's try and understand first why Dijkstra's algorithm does not work if we have negative edge weights. So let's look at this graph where we have one edge from 2 to 3 which has a cost of -5. Now in this graph, if we use Dijkstra's algorithm, at the first iteration we will find that starting from 1, the shortest path that we can find to 3 is the one by the direct edge 5. So we'd say that the distance to 3 is 5. Now, according to Dijkstra's algorithm, once we have established the distance to a vertex, we never examine that vertex again. So henceforth, we will never try to recompute distance to 3. But when in the next iteration actually we compute that the distance of 2 is 7, then we now have the fact that 7 plus -5 is 2. And so there is actually a shorter path from 1 to 3 via 2. But because Dijkstra's algorithm assumes that all costs are positive, it assumes that if it costs more to go to 2 than it did to get to 3 to begin with, then adding an edge 2 to 3 can only increase the cost. So it never looks at this cost again. So the main thing that we need to now do is to recompute minimum costs repeatedly to get around this. Okay, and this is the main adjustment we'll make in Dijkstra's algorithm to take care of negative edge weights. So before we proceed, we should be careful about exactly what we are allowing now. So we are allowing edges to have negative weights, but we should be clear that we should not allow an entire cycle to have a negative weight, because if you go around a cycle that has a negative weight, the cost will decrease. So imagine what happens. So supposing you are at U and you want to get to V, right? And there is a path and this happens to go through a cycle, okay? And this entire weight is actually negative. Then what happens is that each time you go around the cycle, you reduce your cost. So there is no notion of minimum cost anymore, because you can always reduce it further by going around one more time. So if there are negative cycles, the shortest paths are not even well defined. Right? So we cannot allow negative cycles in our graph. So this idea of recomputation can be done systematically as follows. What we do is, for increasing lengths k, we compute the shortest paths with at most k edges. So we first compute the shortest paths to every vertex with at most one edge on the path, then with at most two edges, then with at most three edges, and so on. So to make this idea effective, we use the observation that the shortest path can have at most n minus 1 edges, where n is the number of vertices. Because if we have more than n edges, okay, then we must have a cycle, right? Because there are only n vertices in the graph. And if we have a cycle, we know that the cycle must have a non-negative weight because we have no negative cycles. So we can eliminate the cycle and continue. Right? So if we have a path, shortest path which appears to be longer than n minus 1 edges, it cannot be the shortest path because we can always cut out a cycle and get a shorter path. So now in order to compute the costs for increasing lengths of paths, we can set up a recurrence. Observe that a path of length k from V, the source vertex, to an arbitrary vertex U can be broken up as follows. We first traverse a length of path of length k minus 1 from V to some incoming neighbor W of U, and then we add the edge from W to U. So let us use the notation dist k of U to denote the shortest distance from V, the source vertex, to U, that uses at most k edges. So there are two possibilities. So either the distance with k edges is no better than the distance with k minus 1 edges, or there is a better distance and then it comes through one of the neighbors. So to compute dist k of U, what we do is we take the minimum of all these quantities. We take the k minus 1 distance to U, which we already know, and then for every neighbor W of U, you take this k minus 1 distance to W and add the cost W to U. And among all these different distances, whichever is the shortest one must be the shortest distance using at most k edges from V to U. Of course, we can initialize this by saying that dist 0 of the source vertex is 0. There is no cost. You can go from V to V without taking any edges in 0 time. And for everything else, we can say that the distance with 0 edges is infinity because you cannot go there in 0 steps at the beginning. So suppose we have this graph with 7 vertices with some negative edges. For example, the edge 2 to 5 has cost -1 and the edge from 3 to 2 has cost -2, etc. Now we want to run this algorithm that we just described, where we want to compute the distance from one to every other vertex by increasing order of length. Now since there are only 7 vertices in the graph, we know that the shortest path from one to any other vertex can have at most 6 edges. So we need to run this thing 6 times for k equal to 1 to 6. So we set up a grid like this. So the columns correspond to the vertices. We are computing the distance from one to each of these vertices, and the rows correspond to the different lengths. So we'll first compute all paths of length 0, then all paths of length 1, and so on. So as we said before, we can initialize the 0th step quite easily. Since we're computing distances from 1, 1 is 0 from itself, and everything else is at distance infinity. So this is the initialization step. Now for paths of length 1, what we have to do is take the minimum of the cost of the 0 length path or a 0 length path to a neighbor plus 1 edge. So for 1, of course, there's no change. Now if we look at 2, its cost is currently infinity, but we know that 1 has 0 length path of 0. So 0 plus 6 is the minimum quantity. Similarly for 3, 0 plus 5 is the minimum quantity. For 4, 1 to 4 has a cost of 5, so this is again 5. And now for 5, 6 and 7, all their incoming edges also have cost 0 infinity at this point, so there is no change. Now we come to length 2, right? So for 1 there is no change. Now for 2 we have an incoming edge from 3 which has an existing cost of 5, and since this is negative, this actually reduces. So we have the minimum of the existing 6 and 5 minus 2, which is 3, and so this becomes 3. Similarly for 3, we have a possibility of 5, or we have a possibility of coming via 4, right? And since 5 minus 2 is 3, this also becomes 3. On the other hand, for 4, there are no new incoming edges, so this remains 5. Now we look at 5. Okay, remember we are talking about the previous step. So in the previous step, we could come to 2 with cost 6, or we could come to 3 with cost 5. If we come to 2 with cost 6, then it's 6 minus 1 is 5. If it is 3, then it's 6, 5 plus 1 is 6. So the smaller one is 6 minus 1. So this is also 5. Similarly for 6, the minimum cost is now the cost of coming to 4, which was 5 minus 1. So this is 4. And 7 is still not reachable by a path of length 2. So this remains infinity. So we continue in this way. So now in the third iteration, we find that the cost of 1 doesn't change. But now the cost of 2 reduces by 2 more, because now we can come to 3 with cost 3, and so 3 minus 2 is 1, right? What about the cost of 3? Well, the cost of 3 doesn't change because we've already examined both the incoming edges, and so cost of 4 remains 5 and 5 minus 2 remains 3, so this doesn't change. Likewise, the cost of 4 doesn't change. Okay. Now if we look at the cost of 5, right? The cost of 5 is now the minimum of its existing cost, which is 5. The cost of coming to 2, which has reduced to 3. Remember, we are looking at the previous row. So it's 3 minus 1 is 2, or 3 plus 1 is 4. So clearly among these, 3 minus 1 is 2 is the shortest one. And for 6 there is no change because the distance to 4 hasn't changed. So this remains 4. But now we can compute a distance to 7. So 7 is either the cost of coming up to 5 in the previous iteration, which is 5 plus 3, 8, or coming to 6, which is 4 plus 3 is 7. Okay, now we keep going. So at the next stage, again, the cost of 1 doesn't change. Now the cost of 2 hasn't changed because the cost of 3 hasn't changed, right? So this remains 1, this remains 3, this remains 5, okay? And now we look at the cost of 5. So 5 was earlier 2, right? But now we find that the cost of coming up to 2 is actually only 1. So we can come 1 minus 1 and we can make this 0. Okay? And now we look at the cost of 6, it doesn't change, right? Because the incoming edge is from 4, which hasn't changed. But if we look at 7, so 7 has an incoming edge from 5. Earlier we had computed it as 5 plus, we had computed it as 4 plus 3, 7. But now since 5 has reduced to 2, we can compute it as 2 plus 3 and we can get 5 over here. Right? So because the existing cost for 7 was 7, and the other possibilities are to come by a 6, which is 4 plus 3, which is 7, so there's no change, or come by a 5, which is 2 plus 3, which is 5. Okay. So we keep going. So after 5 edges, there is no change to 1, there's no change to 3, there's no change to 4. Okay. Now when you come to 5, because 2 didn't change, this doesn't change either. When you come to 6, okay, because 2 didn't change, 4 didn't change, this doesn't change either. But on the other hand, if you come to 7, because 5 reduced in the last iteration from 2 to 0, okay, this has now become 0 plus 3, which is 3. Right? And now, sorry, there was a mistake in this row, but just by copying, so that should be a 5. Right? And now, actually, if we do one more row, we'll find nothing changes. So this is the final distances that we get with at most 6 edges, which is the maximum we can use without having any loops. So this is what the algorithm formally looks like. So this is an algorithm which is called the Bellman Ford algorithm after the two people who discovered it. So V is the source vertex, N is the number of vertices. Okay, cost is the edge cost. It's the adjacency matrix with cost, or the cost of every edge, depending on how you are representing the graph. Dist is the distance to every vertex, which we are going to compute from V. So we initialize it. So as we described, we initialize it by setting up the cost with paths of length 0. So for every vertex other than V, the cost is infinity. For V itself, the cost is 0. And now we do this loop n minus 1 times. So n minus 1 times we pick up every vertex u. Now we have to be a bit careful because in that, as we saw in the iteration, we have to keep track of the previous row and the current row. So inductively, dist of u is up to k minus 1. And this is going to be the new thing that we're computing up to k. So we have to run through every possible edge and compute the minimum. So we initialize the k distance for u to be the k minus 1 distance for u. Then for every incoming edge, if we find a smaller distance than the current k distance, we update it by taking the minimum of the current distance and the distance to the incoming neighbor I plus that edge. And having done this for all the vertices, then we just replace, right? So we put back the values into the dist matrix and go back to the top of the iteration. So now dist has the values for k, and we do this from k equal to 1 to n minus 1, and we're done. So the complexity is fairly straightforward, right? So we have an outer loop which runs on times, right? And now we have to do this processing for every vertex, and if it is going to be using an adjacency matrix, then this is going to take time O(n) squared, because we'll have to scan every vertex and then scan every row in the matrix for that vertex. And if we are doing adjacency list on the other hand, right, then this is going to take only order m time, because in every scan of this we look at every edge exactly once. So this whole thing, this whole inner loop takes om time. So therefore we now can say that the complexity is either order n into n squared, which is n cubed, or it is nm, depending on which representation we use. So if we use the adjacency matrix, it is going to be n cubed. If we use the adjacency list, it's going to be order n times n. So there are a couple of optimizations that we can use to reduce the running time of this algorithm. So the first is that, as we saw even in the simulation we did by hand, at k plus 1, the only distances that can change are those whose incoming edges changed in the previous round. So in each round, if we maintain a queue of those vertices whose distance have reduced in this current round, then in the next round, we can use this queue to selectively update only those neighbors of vertices in the queue. We don't have to look at any vertex whose neighbor doesn't appear in the queue. So from this, it follows that if there is no change observed for some iteration k, then there will be no change henceforth. So we don't have to run all the way to n minus 1. We can just terminate the entire algorithm right away. So to summarize, what we have seen is that Dijkstra's algorithm for the single source shortest path problem does not work if we have negative edge weights. But we can use a dynamic programming algorithm due to Bellman and Ford to solve this problem even with negative edge weights, provided there are no negative cycles. If there are negative cycles, then the problem of shortest paths is not even well defined because we can go around and around the cycle and keep reducing the path indefinitely. And the complexity of the Bellman Ford algorithm, if we use the naive adjacency matrix representation, well, it's order n cubed. And if we use adjacency lists, then the complexity is order n times m.